So now we bring one more variable into the equation of weather. We're going to talk more this week about moisture. Moisture being described in humidity and saturation. However, as part of moisture, it affects the stability of the atmosphere. And we'll talk about that this week, and we'll begin to learn. You're going to see that a lot throughout the rest of the course. So, how does the cycling of the water in the Earth's atmospheric system help maintain a habitable planet? Well, we need water to live, that's for sure. So, one of the classic examples of water moving around is an atmospheric river. Atmospheric rivers can develop over the Pacific. You see one right here. Stretches from the tropical southwestern Pacific all the way into Northern California, Oregon, Washington. And that's an area with very high amount of moisture, and it's just flowing right into that area, and it can bring a lot of rainfall to that part of the world. Here's an example of that, all that moisture being transferred inland, rising up, causing heavy snow on the mountains. Might even flood rivers. So the total amount of the water in the atmosphere is relatively small, generally less than 4% by volume. And most of the time, it's a lot less than that. In the winter, it's going to be significantly less than that. So if all water vapor were removed at any one point in time, if you average it over the world, you'd have about a depth of about 1 inch of water. So if every ounce of water, if you had a normal day and every ounce of water was dumped out, it would be 1 inch. So water is continually entering the atmosphere from lakes and oceans, even plants. And the atmosphere brings it back to the lakes and oceans. Here's the global water cycle. Lots of evaporation over an ocean, lots of precipitation over an ocean. But guess what? More water evaporates than actually falls by precipitation over the ocean. So that water comes inland, becomes mountains, hits mountains and runs off fast on the mountain slope. Maybe it hits the flat valley somewhere and lays there. Oh yeah, and then plants are going to allow it to evaporate, and they actually through photosynthesis release water vapor, particularly in the afternoon and evening hours. And some of this water makes it back into the ground and goes into groundwater storage. Others just run off, especially if you have a road, you can see it run off very quickly. But all of it, that's your whole water cycle there. So there's evaporation, which basically heats up. Molecules are being heated up so that they can enter as a vapor back into the clouds. Condensation, when molecules return to water. Transpiration is water taken up by plant roots, which escapes as a vapor. So the total of transpiration and evaporation, which might go into the atmosphere, is evapotranspiration. Sublimation, ice or snow becoming a vapor, and then vapor becoming a solid without going through it. So precipitation occurs in water, either in liquid or frozen form, that falls back down to the ground. So the question becomes just how humid is it outside? How much moisture is out there anyways? It varies from every single day to every single minute in the day. And there are various measures of moisture, and each one has a purpose for meteorologists, and you're going to learn a little bit. Vapor pressure. Water vapor is a vapor, so it exerts a pressure just like any other gas. Mixing ratio. Basically, it's looking at the total amount of water in a certain amount of air. Specific humidity, absolute humidity, relative humidity, dew point, precipitable water. All terms you're going to see this week. So vapor pressure, like I said, it's generally less than 4% of the atmosphere. So as vapor pressure increases, the amount of water increases. Mixing ratio, it's just the mass of water vapor per the mass of remaining dry air. Notice that here it differentiates the mass of dry air, while a specific humidity is the mass of water vapor per the mass of all the air in it. This includes the mass of water vapor as well. And absolute humidity is the mass of water vapor per unit volume of unit air. So how do we determine when air is saturated? You look outside, and some days it is not a cloud in the sky. It's pretty doggone dry, isn't it? But the humidity could be still high, but it's not saturated. Saturation is there different phases of it. Saturation, vapor pressure, saturation, mixing ratio. And it's basically the point at which that air can hold no more water. So hotter the air is, the more water it can hold. So if you're in the middle of winter and it's 10 below zero, guess what? It's not holding a lot of water here. The saturation vapor pressure to saturate it is 1.25 millibars. However, if it was over ice, which that temperature could be, it's 1.03. So it can really, you can see the saturation vapor pressure over ice is actually lower than over water. That's going to be a big thing to learn for later. But right now, look at that difference. Wintertime, 1.2. Summertime, 56 millibars. 50 times more just for heating up the air. That's how much water that air can hold of water. It's not how much is necessarily in the water. So relative humidity is what we're all used to hearing. It's basically vapor pressure for saturation vapor pressure. So we just solved the saturation ones there. If we could measure vapor pressure, you could come up with relative humidity. Multiply it by 100. So if it's 100% relative humidity, the air is saturated. If it's 50%, well, then it can hold 50% more. Relative humidity varies by temperature. So the cooler mornings, relative humidity is going to be higher. Even if the amount of moisture didn't vary in the air, the relative humidity will be higher in the mornings. That's why you have fog in the morning. By afternoon, however, temperature gets hotter and the relative humidity actually drops off. And it starts coming back in the early evening. And a lot of times the dew points start coming back then, or moisture starts coming back in from evapotranspiration of plants. Dew point's another measure of it. It directly measures water vapor content of the air. The greater the concentration of the water vapor, the higher the dew point. So let's take it in the summertime. Dew points sometimes in the summertime reach into probably the low 70s in Ohio, maybe the mid 70s on a really, really humid day. That's a lot of moisture. Temperature might be 90 degrees that day, so it's not saturated, but that's a tremendous amount of moisture. So dew point is basically the temperature that the air cools to so that it becomes saturated. So in that case, if it was 85 degrees out, the temperature and the dew point was 75, if that temperature cooled 10 degrees, you would have saturation and literally see dew form on the ground. You can see the huge difference in the summertime. Notice that the Rockies, boy, almost like a dividing line right there. It's a lot drier out there in the summer. And guess what? There's a lot more forest fires and all out in California because it's drier. More humid down here, definitely down towards along the coastlines. So humidity can increase in a couple different ways. Air is cooled, so saturation vapor pressure will decrease. More moisture, evaporation occurs, so you wind up increasing the vapor pressure, getting close to saturation. So now we're going to talk about stability. What is stability? Think about a hot air balloon. It's not that big, right? But you have air all around that hot air balloon. Well, think of an air parcel the same way. You have air all around that air parcel. So we're going to take that air parcel, and for whatever reason, a mountain or whatever, we're going to start lifting that air parcel. If the air parcel is colder than its surroundings, air, and the air around it has maybe a temperature of 5 degrees Celsius, but the parcel has a temperature of 3 degrees Celsius. That parcel, even if it's lifted, is going to try to accelerate back downward. So that parcel would be stable. Now, let's lift another air parcel, and we'll say that air parcel is actually warmer than the surroundings. Say it has a temperature of 10 degrees, and the air around it is only 5. Well, it's 5 degrees warmer. that air parcel is going to want to rise. And the more that temperature difference is, the faster that air parcel is going to rise. The more it's the other way, the more it's colder, the faster that air parcel is going to sink. So there's things called absolute instability, where the air temperature is dropping more rapidly with altitude than the dry adiabatic collapse rate. It doesn't happen much. Conditional instability, and that's where moisture adds in. Remember, if you release latent heat, you go on the moist adiabatic collapse rate. There are some lifting processes that occur. We have convection. The sun heats the air, gets unstable, and lifts. You might see this along the shore of Lake Erie in the summertime. You can have fronts. Remember, warm air is lighter than cold air. And when you add moisture into it, it's even lighter. So the warmer air is always going to be either above a warm front as it's advancing. The colder air will be underneath it to the north, and the warm air will lift over top of it. And we had that here at my house this last week with overrunning, had over 5 inches of rain. And then you have the cold front coming in, and the warm air is still going to be riding up and over it, but the cold air is moving southward and replacing the warm air. Orographic lifting, the mountains can do it. And if you reach a lifted condensation level, we're going to talk more about that in convection. That's the level where the moisture saturates the air, becomes saturated, and all of a sudden it starts following the moist adiabatic collapse rate, and that can change everything. There are rain shadows. If you happen to live in West Virginia or in the mountains, think if you have an east wind in West Virginia, the air is going up, up, up on the east side of the mountains. On the west side of the mountains, it's kind of falling down. It got drier. It heats up. Surface winds converge with lifting. So let's take a look at just a couple things here today. Here is a moisture pattern for today. You can see dry air out here coming up out of the desert southwest and in. You can see moisture down to the south, and a lot of moisture down here by Beta, a lot of green off the Gulf of Mexico. Less moisture, but moisture coming in off the northern Pacific here, coming inland. This is Teddy out here moving upwards away from the coast. You can see another little band of moisture coming down where it's very cold. So the amount of moisture is very different between these two. But this is just the mid-level of moisture. So say we were looking at a front. The front's actually down here south of the Gulf Coast right now. Moved down there. So if we looked at a Stuvie diagram for Tallahassee, what do you see here? Well, if we lifted this parcel of air, and it follows the dry adiabatic, which is this blue line. It goes like that. That parcel of air is going to always be stable, right? But say I push that parcel up so that all of a sudden I'm lifting it right here, and it becomes saturated. Whoa. Now I'm following this dashed line, and look how much further over I am away from the temperature curve, and all of a sudden I'm unstable. This is a conditionally unstable sounding. And this is the thickness of that cold air. You can see the east winds here, and they shift to southwest right here. So the cold air is all down here. I wanted to show you exactly the same sounding, but I want you to see it in a different way. These are called skew T's, and there's a reason they're called skew T's, because the temperature is skewed to the right. Here's minus 10, 0. Looks a lot similar to the previous one, but this is what I'm used to looking at, because it gives something called convective available potential energy that I can directly read off of it. But it has precipitable water here too. So if you were to take this, every ounce of water out of this, 1.62 inches of rain would fall in Tallahassee right now. So, just some things about moisture you can see today. And if you look back here at dew points, for example, look at the dew points up in Ohio right now, in the 30s, 37. However, you go down here, dew points are 74. A lot more moisture down here than up here. just by looking at dew points. And remember, the dew point is the lower left on the station symbol. So let me know if you have any questions about this.